4.2, the mean value theorem, part 2. Your objectives for this lesson are to apply the mean value theorem and to find the antiderivative of a function. Okay. So as you can see, functions with f prime equals 0 are constant. We've been over this a few times, so if I had f of x equals 7, my derivative is 0. 7 is a constant. If f prime of x equals 0 at each point on an interval I, then there is a constant c for which f of x equals c for all x in I. This is just going the opposite way. So instead of going from, back up here, f of x equals 7 to f prime of x equals 0, you're moving from 0 to 7. Functions with the same derivative differ by a constant. If f prime of x equals g prime of x at each point on an interval I, then there is a constant c such that f of x equals g of x plus c for all x in I. So for instance, if f prime of x equals 0 and g prime of x equals 0, then, I don't know, maybe f of x equals 6 and g of x equals 10. Well, really, in this case, and just in this case, f of x equals g of x minus 4, because we would subtract 4 to get that 6. Example 6. Find the function f of x whose derivative is sine x and whose graph passes through the point 0, 2. Well, this is simple enough. So basically, we have to ask ourselves, who has the derivative of sine x? Well, I know that the derivative of cosine x is negative sine x. So therefore, the derivative of negative cosine x is positive sine x. So if I had a function g of x that was negative cosine x, I know that f of x is going to be negative cosine x plus c. This is because since they have the same derivative, the functions only differ by a constant, c. To figure out what that constant is, we have this little helpful tidbit that the graph passes through 0, 2, which means that when x is 0, y is 2. So basically, f of 0 equals 2 means that 2 equals negative cosine of 0 plus c. Cosine of 0 is 1, so this is negative 1 plus c. When I add 1 to both sides, I get c equals 3. This leaves us with the information that f of x is negative cosine x plus 3. The process that we've just gone through here is called finding the antiderivative, so antideriving. A function f of x is an antiderivative of the function f of x if big F prime x equals little f of x for all x in the domain of f. So since the derivative of f of x, the big F of x equals the little f of x. When you don't take the derivative of the big F of x, you get the antiderivative. So the process of finding the antiderivative is called antidifferentiation, antideriving. Example 7. Find the velocity and position functions of a freely falling body for each of the following sets of conditions. A. Acceleration is 9.8 meters per second squared, and the body falls from rest. Okay, so we know that acceleration is the first derivative of velocity. So when we're anti-deriving this here, we're going to be finding velocity first. So v of t equals 9.8 t plus c. And since we know that we're starting from rest, the velocity is 0 at time 0. So v of 0 equals 9.8 times 0 plus c. Okay, so 0 equals 9.8 times 0 is 0 plus c, which leaves us with c is 0. So that means our velocity function, v of t, equals 9.8 t. That's it. The position function, we're going to have to antiderive our velocity function to get the position function. So I know I'm going to have to, let me move this out of the way first. I know I'm going to have to go up 1 power, just like when I'm deriving I go down a power. So I'm going to go from t to the first to t squared. I also know that usually I bring down that power. So what I'm going to do to find s of t, I'm going to divide 9.8 by 2, so divide that by 2. That's going to give me a 4.9 t squared plus c. Plus c. But again, so we have s of 0, time is 0, equals 9.8 times 0. So our velocity was 0 at time 0 plus c, so that all goes away. And again, we have just a c equals 0. Okay, so we got our velocity function was 9.8 t, and our position function, s of t, is 4.9 t squared. So pretty easy when you're starting from rest at time equals 0. Let's look at a different scenario. So again, the acceleration is 9.8 meters per second squared. The body is propelled downward, this time with an initial velocity of 1 meter per second. So let's see what's changed here. So at time equals 0, our velocity is 1 meter per second. So plugging back in, 9.8 times t is 0 plus c is now going to equal 1. That goes away, and I get c equals 1. If you're wondering where these numbers just came from, remember we had the formula 9.8 t plus c. So this is our velocity. So now we end up with, I should say, v of t, 9.8 t plus 1. Okay. And our position function. So position, I already divided that by 2. So s of t is going to be 4.9 t squared plus, now this 1, I need to give that a t, so plus t plus c. Okay. And I know that I'm starting at 0 when time is 0. So s of 0 equals 0. So 0 equals 4.9, 0 squared plus 0 plus c. These go away. C equals 0, which I can plug back in. So s of t is 4.9 t squared plus t. Technically plus c, but we're just going to leave it like this. So here's our velocity and position functions. Oh gosh, that's it for 4.2.